Hello, everyone. Welcome back for another round of Logos team updates. These are all hands presentations effectively so that we don't have to spend time on our one day of all hands going through them. We can all do it beforehand and then spend time together talking and doing other things. So this time around, we have David and Moody to talk about blockchain and LEZ or LEE, Logos Execution Environment. Up first is going to be David talking about Logos blockchain. So take it away.
Great. Okay. So I'm David. I lead the blockchain team here. I'll talk about the blockchain and Woody will talk about LEZ afterwards. I've spoken to quite a few people about blockchain and tried to get their thoughts on it. And I think a lot of people don't understand what Logos blockchain is and how to program it. There's a lot of uncertainty about like what is the actual, like how would you actually use it, because we have no programming model, right? We don't have any VM. What we're trying to build. So besides the team update, I want to also give like a bit of background on what Logos blockchain is and try to get that context out there so people understand what we're building better. So we're trying to build a neutral permissionless settlement layer for decentralized applications. So breaking that down, neutral is just a positive framing on censorship resistance, right? We want to have, we want to make sure that there's not any one node who has too much power, and there's not too nodes are free from coercion. They don't feel like they have to restrict themselves when they participate, and they're not worried about being attacked or targeted in any way. Permissionless, we want to make sure that there's very low requirements to join into the Logos blockchain. Other protocols have quite high staking requirements or node requirements. We want to avoid all that. We want very low. We have no stake requirement. You can participate with no stake, with one token, and there's very low hardware requirements to run a node. And so settlement layer, what we're referring to here is the distributed logs that decentralized applications generate when they run. So that's transactions that are getting done in order and settled into the blockchain. So replicated logs are the foundational component of many distributed systems. You see it in databases, the bin logs that are replicated from primaries to replicas. And you see it in Kafka, these queuing systems. So that is what we want to provide. We want to provide a replicated log that is maximally resilient, and anyone can participate in this system. So the way that we achieve this is through two prongs: private proof of stake and a very minimal execution layer. So private proof of stake is how we make it very easy for nodes to participate without risk. And the minimal execution layer is how we prevent censorship, how we prevent our network from centralizing too much. We want to be free of MEV as much as possible. And I'll just contrast with other systems, like for example, Ethereum. Ethereum decided to go into this proposer build PBS architecture, proposer builder separation. So you have builders operating separately from the validators, block builders I'm talking about here. So the Ethereum has what, 1 million validators now, and each of these validators pull blocks from these block builders who are producing the actual blocks that are filling the Ethereum blockchain. If you look at the analytics, you have a single entity, Titan, producing 51% of the blocks in Ethereum. So despite like a highly decentralized validator set, there's one entity who is producing more than half the blocks. So like this is like a highly centralized system, in my opinion, and this is something we do not want in Logos blockchain. So to reject this end state, we take the opposite, right? So Ethereum has a very rich L1, right? The EVM is very rich. You can program it with all sorts of contracts, and you have Uniswap there. So this richness attracts MEV. And so we take the opposite approach. We have a very minimal execution environment that just has the minimal operations to run a zone. Back to PPOS. So our implementation of private proof of stake is through, it uses two components, Cryptarchia and Blend Network. So Cryptarchia is our consensus protocol. It's a Nakamoto-style consensus protocol that uses a private stake lottery in place of the hash lottery from Bitcoin. It has permissionless participation, like I mentioned, zero stake requirements, so you can participate with, one token, and there's no slashing here. Blend Network is so Cryptarchia alone is not sufficient to provide private proof of stake, because despite being a private stake lottery, anyone who's observing the mempool is able to triangulate the block producers. You can find out which IP is generating the blocks. From that, you can determine how much stake they have by watching the frequency of blocks they produce. So just Cryptarchia alone is not enough. On top of that, we layer the Blend Network, which is an anonymization protocol for the network. We route all of our block proposals through the Blend Network. And we do this to protect all the nodes that are participating in consensus. This obscures the sender receiver. So the people who receive a block proposal cannot link back to the proposer easily. They'll have to break the Blend Network to get that. So why do we do this? Why do we try to do PPOS? The end state is that we take on a lot of complexity into the protocol, and the outcome is a very low stress, low overhead node operation result for end users. So you running a node are not exposed to the wild network, wild internet, right? You're not worried about people finding out that your node has all this stake inside of it and being a target of hackers. And you're not worried about your network going down, your node going down, consensus bugs in your client, things like that, because there's no stake, there's no slashing. So if it does so happen that your node is down, you might lose some block rewards, but you won't be slashed. So it's a very low overhead from node operations point of view. So back to the programming model. So we have this very minimal execution model in the blockchain, and that's using channels. So zones use channels to post inscriptions on the Logos blockchain. So these channels are hash parent ordered inscriptions. It's effectively a virtual chain on top of the Logos blockchain, a virtual blockchain. The contents of these messages that are posted in these channels are just opaque binary blobs. We don't do any execution on the Logos blockchain. So you can bring your own VM. You can select your own transaction model. For example, LEZ has a very sophisticated transaction model that supports, ZKVM proofs. It's a something that you could not do in, for example, if you're trying to program this on top of like a very rich L1. It'd be hard to try to code up the rules of LEZ in Solidity, for example. So this gives the freedom to the zones to select their own transaction model, their own VM, and leaves the L1 free of taking on any complexity for selecting a VM, right? When you select a VM, you're locked into that model. So that's a high-level overview of the Logos blockchain. I wanted to give a quick update on what we've been working on in the past couple months, and how any big decisions we've made, and what we'd like to do in the end. So, going forward. So the largest change in our design has been the fact that we're no longer targeting DA for mainnet. So that was a large change. It was a difficult decision to make because we put in a lot of effort towards DA, both in research and in implementation. But the way we see it is that DA is a scaling solution, and we should bring it in when we have scale. And if we try to do everything at once, for example, we're doing a new consensus protocol, Cryptarchia, blend network, which is the whole anonymization network. If we try to do DA on top of that, that's 3 separate distributed systems that we're trying to design, debug, implement. And we likely won't be able to do all 3 of them at a high level of quality. And if we don't have the scale to require DA in the first place, then it's a lot of lost effort towards something. It's not the right use of time. That said, we're still doing active research towards DA, and post mainnet, we will bring back the next generation of DA that we've developed up to that point, and we'll try to integrate that back into Logos blockchain. We've run now 7 quite productive devnets. Each of the CCs are running their nodes on their Raspberry Pis, and we've had some nodes from DSD Lab join. We have 4 nodes running on the infra fleet. We've had the longest running devnet was 4 days. That's not to say that we could not have gone long. There was a few devnets that were just too stable, and we were not learning much from letting them go, so we cut them off early. But they've been quite productive. We've found many bugs, and we've resolved many issues. We've developed a Zone SDK, and I'll be doing a demo after this to show off one zone that we've built with this SDK. And we've developed the Logos Core blockchain module, which has successfully connected to one of our devnets and synced with the chain. This is what our blockchain node currently looks like. We have the ability to start the node. We can inspect the balance of the keys in the wallet, and we can do transfers. These are like Bitcoin style transfers with UTXOs. So you can start the node, stop the node, and do transfers. That's basically all we're going to support for this first V0.1 testnet. Yeah, so with that, I'm going to do a quick demo of our zone SDK, what we've been calling the SQLite zone. So the reason why we wanted to do this is that SQLite is a well-deployed database. There's hundreds and thousands of open source applications that use SQLite. And they all have the problem of how do you sync? your database. Like if you have a password manager locally on your device that uses SQLite, how do you get that data to another device? And so we developed a zone that intercepts the SQL transactions to SQLite, posts them to a channel on Logos blockchain, and then replicates them to any node that's following that channel. And I'll do a quick demo of that zone now. Hopefully everything works. So we have a blockchain node running here. I have a block explorer here that's following the blockchain node. You can see the current height increasing. I'm just going to wait to make sure. Yeah, it's increasing. Okay, great. And so now I'm going to start the sequencer for the SQLite zone. Okay, great. So you can see that the sequencer started up, and it saw that it previously did not have a channel, and so it created a new channel by just generating a random channel ID. These channels are very lightweight. You can just generate them by just writing to an empty channel ID. And now it's listening for SQL commands. So this SQL database has one table in it, and it's called menu and menus. And it lets you write items to the menu. So here, let me just start up the other terminal here. Okay. Okay. Here, so I'll first write a message. I'll do a SQL transaction on the SQLite zone here. So I'll do an insert into the database. So insert into menus, values, and then we want to write what we want to insert. So these are the items on the menu. So I'd say Jello extra jiggly. I think I got that right. Menu, maybe it's menu. There it is. Okay, so I've written to a SQLite database here, and the SQL Zone SDK intercepted the transaction to the SQL database and then wrote it to a channel on the blockchain. So here we just had a block, about 5 blocks back, that has the inscription that writes. If I inspect the transaction here, you can see the SQL transaction that was written to the channel. Now I can set up an indexer that will follow that channel. So I'm going to copy the same channel ID, and I'll just set it here. Okay. Oh, I missed the. Oh, there it is. Okay, great. So now this indexer is going to follow this channel that we specified and listen to new SQL transactions that were posted there and apply it locally to their own SQLite database. So I think it's synced by now. I'm gonna do a select star from menu. Okay, it's synced, great. And so this is actually running against a real SQLite database. It's not, there's no hacks here. So I'll just do another insert here. Revenge. Okay, so now we're going to go back. Okay, it's already there. So the node accepted the inscription, produced a block, and you can see the SQL transaction was posted into the inscription of that operation, of that transaction, sorry. And now if we query the menu again, you can see that it saw the write to that channel and applied it to to its own SQLite database. Yeah, so that's the end of the demo. So why is this cool? So there's, like I mentioned, there's like thousands of SQLite open source applications. For example, there's one open source password manager that's written in Rust that uses SQLite, and it writes the passwords encrypted into SQLite. That's a local application that cannot sync to your device, right? So imagine you run one of these Logos blockchain nodes on your device, on your phone. These are very lightweight nodes. It's easy to run. You get syncing for free by just using, well, not free, but you get to do very low effort syncing of your state across all these devices that you own. So this is kind of compelling to me because I think we can, there's a whole group of people who just want to do syncing of their state, and they can do it through this method. Yeah. Okay, I think that's all I want to say about that. So looking forward, things that we want to build before mainnet. We want to add support for decentralized sequencing. That's so for example, in the case that I just showed you, there was a single writer to the SQL database, and then there was many readers, right? But in the final version, it would be great if we could have multiple devices writing to the same channel, and they all can sync with each other, and you can resolve the conflicts about reorgs and things like that. So we will support decentralized sequencing for mainnet. Hopefully, we'll have it ready for the June testnet, but I'm uncertain if we can have that ready. Bridging. So we'd like to have support for bridging the Logos token from L1 up to the zones and back. Currently, for this first testnet, we're going to be minting Logos tokens both in LEZ and on the L1. So these are two decoupled tokens. We don't do any bridging between the two layers. And we'd like to add support for some cross-zone messaging. This would allow you to do things like a state change in LEZ, like somebody getting added to a DAO or something like that, would trigger a policy change in your SQL password manager that adds that person to your password manager group, and they have access to your passwords, things like that. So we have a design that supports both synchronous and asynchronous messaging. So we'd like to add support for that before mainnet. Yeah, so that's it from the blockchain side. So I'll hand it off to Moody from here, and he will talk about the LEZ.
Hey all, thank you, David. So yeah, today I'll be talking about the Logos execution zone and the Logos execution environment. First of all, I would like to thank the Red team, EcoDev team, Smart Contract team, and everyone that was contributing in writing programs and helping in doing cool stuff on LEZ. So thank you all. So yeah, I will give just a small presentation about what LEZ is currently. What was the last status when we presented about our work? It was September. What changed since then? And if there will be a little bit more time, I will show a small demo about our block explorer. So the Logos execution zone is a programmable blockchain with public and private state working together. We offer protocol level privacy. So developers have to write the same app logic if for public or private inputs. And for privacy, we are using the RISC-0 ZKVM to generate ZK proofs. So why Logos execution zone? How I like to picture it and tell people about it is that the Logos execution zone actually, it keeps the composability of the public chain, but it also adds privacy by default. In our case, we also have selective privacy that I will talk about later. But whoever is using the Logos execution zone can go from fully private to fully public, or to use some shielded executions or not. So there is a choice for the user when to be public and when to be private and what to show. So we have transparency because the public state is visible and can be audited. We have privacy because the private state is hidden, but it can be verified. And we have interoperability between the states because the same apps can touch both states without having to deal with like special handling or do complicated transactions. So as I said before, we have two parallel states, one public, one private, but we have only one execution model. So the public state, you can see it as an on-chain mapping from ID to account state, and it's fully visible. While the private state, it's commitments and nullifiers. So the values actually are hidden within commitments, and only whoever has the viewing keys can reveal what is hidden in those commitments. So the private accounts actually is, as I said before, you have hidden values, but you can verify them. But what you can also do is for each update, like for each commitment, you cannot spend it more than twice. So when you have a commitment and you spend it, then you will nullify it. So for every commitment, there will be a nullifier that will spend this commitment. So as you see in the first diagram, we have the first commitment, which is now old because it was nullified, it was consumed. The second one is consumed, so it was nullified and it has the value N2, and now the current one is C3. Only the holders of the viewing keys can read the private or the hidden values, and we use nullifiers actually, as I mentioned before, just to prevent the ability to reuse the same old private state again. So what we really focus on is the ability to write programs without caring a lot about the privacy, because the privacy is handled on the protocol level. So the programs treats accounts uniformly, private or public, and the protocol is where all this privacy and magic happens. So our programs are stateless, so there is no internal state. The data is stored in accounts, so you have accounts that are executed. The developers need to write only normal program logic. They should be explicit about the account inputs, and they use the same code for either public or private state. On the protocol level, what we do is that we enforce the privacy, we prove the consistency, and we preserve the composability between the two states. So in this model, we have two execution types, but the same bytecode. So the public execution is on-chain, is using the RISC-0 VM, and it has there is no need for zero-knowledge proofs, while the private execution actually is executed locally off-chain on the user device. Then the user can generate a ZK proof, and this ZK proof will be then verified by validators on-chain. So what we get from this, we get efficiency because we have fast public executions and light validators for private executions. The only computational cost for private transaction is the user device. So it's just the proof generation on the user device. And then this proof will be verified by the validators on chain. So we have fast public transactions because we don't require any zero-knowledge proof. We have parallel-friendly environment because the account-based model actually supports parallel executions. And we have composability by default because within the same app, we can mix between public and private accounts, between public and private executions. So what you can build on Logos Execution Zone. Actually, the main thing that we thought about when we were building all this project is the ability to give the same services that are delivered by transparent blockchains, but also with some privacy preserving features. So anyone that is using Logos Execution Zone can build apps that can span transparent and privacy preserving accounts at the same time without having to rewrite the logic. Some example could be private payments, where the sender or the receiver, they don't want to reveal their balances on chain, or where the receiver, the sender won't reveal any information about the receiver. It can be used for confidential DeFi. In this example, we have the AMM program where someone can trade with private positions while staying composable. So the ability to do private swaps on top of a public AMM. And what we offer is the selective disclosure. This is what I talked about before, saying selective privacy. So users can either choose the level of privacy that they want, depending on what they are doing at the moment. Plus, they can choose to reveal only what is necessary. So, as I said, everything is hidden, but it's auditable. It's verifiable. So if, for example, I need to, for example, I'm using a voting program and I want, I want to do it privately. So what I can do is that I can show that I have executed the program and the vote correctly, but I can still choose to hide my identity. At a later time, I can just say, okay, I want to reveal my identity, and ID shield this transaction, and I say, okay, I voted this, or I was the one that has this vote ID, and that's it. So the core thing that we can take from the Logos Execution Zone is that we can write the program once, and we can run it publicly, privately, or both at the same time. So, as I said before, I will talk now a little bit about the updates that we had. So, in the last IFT call in September, the architecture was like this. So, we had public-private states, we had privacy-preserving circuits. Our wallet only supported public native token transfers, and we had a centralized sequencer. So we still have public and private states, we still have privacy-preserving circuits. Regarding the wallet, I will talk in the next slides, and we still have a centralized sequencer. So currently, these are the main changes from the last update. So now we have a full integration with the Logos blockchain, meaning that our sequencer posts LEZ blocks on top of the blockchain. We have an indexer that can parse these blocks from the blockchain, and we have a block explorer that can show every transaction, every hash, every block ID, every account ID, everything that is happening, it can be shown. I will show a small demo later. Now our wallet supports way much things than before. So now we support public and private native token transfers, public and private custom token transfers, we have the Piñata program, which is the wallet faucet, where the accounts can claim funds. We added all the privacy preserving features for the wallet command. We have written an AMM program, and all these programs that have been implemented are fully programs, not only features. So we also added in our repo program deployment and wallet tutorials, and these will be also shown in a workshop during the Parallel Society. What else we have worked on are the token program design. So now we are able to create and transfer custom tokens, as I said before. It supports NFTs. It is a fully working version, but it has some limitations. So for now, to create an account, there should be a fixed supply, and we don't support yet the freezing mechanism. Regarding AMM program, we have implemented a very basic AMM program that doesn't support fees for now, but at least it supports the main function. So one can create a pool, add, remove liquidity, and do swaps. We also worked on tail calls. So we designed and implemented tail calls, let's call them cross calls. So these are a general mechanism for any program that needs to interact with other programs. It's like chaining calls to other programs. And this was motivated initially by the AMM swaps, because these swaps, when are executed, transfers are made by other programs. But it's not only for that, but that was the motivation. So currently, our AMM is built on top of the token program, and tokens are generally managed by the token program. So the AMM program needs to execute the token programs internally to do swaps. And to do that, it needs the cross-call mechanism so it can execute the token program. Beside this, we also worked on PDAs, program-derived addresses, and we implemented them for public state only for now. And that was also motivated by the AMM program because actually the AMM program need to hold the tokens of the pool. So we needed to find a mechanism that can hold the state of another program, which is the token program. Without the PDAs, the remaining tokens can be transferred via direct transfer. So we use the PDAs actually to give the ability to the AMM program to hold the tokens that are not held by any other user. So whatever remaining in the pool through the PDA, the AMM program can hold them. So we also worked on some challenges that we found a solution for them, but we didn't have time to implement them because we gave more priority now to the full integration with the Logos blockchain. So we worked on cross calls to support mid calls, and that was motivated by some examples as flash loans and flash swaps. So whenever we need to support these programs, we need to also support cross calls in mid calls. So we investigated this. We found a solution. It just needs to be implemented. We also worked on block context. And actually, this is because when we were writing programs, we wrote the specs for voting program. We didn't implement it, but the specs are ready. And yeah, so we need for some programs, we need to know the exact block range. So we investigated block context, and we found a way to do this, to add this to our architecture. This will be implemented in Q2 as well. Right now, private accounts, if they want to receive funds privately, they cannot do it. So every time we need to create a new account, send funds privately, and then the receiver can claim it. We found a way to allow sending funds to already existing private accounts through execution continuation. This will be also implemented in Q2. And right now, private accounts cannot be shared. Like accounts actually cannot be shared by multiple users. So we investigated and we researched a way to make it possible. We found a way to allow multiple users to share the same private account. And this can be thought about like if we have a private pool for a private AMM. It still needs some refinement. We investigated like 2 or 3 approaches. We settled on one approach, but we still need to find a way to minimize the changes to the core of the architecture. What we didn't look at yet, but it's on our list, is the contention problem and the decentralization of the sequencer. So yeah, from the last all hands till now, I think we changed a lot of things. We improved a lot of things. We are happy that now we have full integration on Logos blockchain, and most importantly, we are seeing the real use of LEZ. The smart contract team and the EcoDev team are doing a great job. Thank you again. And yes, if I still have some time, I just would like to show you a small demo that I started already, so it will be fast. I will share my screen. Okay, so so there is a lot of things. There are a lot of things going on, but I will be brief. So we have the Logos node that is running. We have our sequencer that is posting blocks on top of the blockchain. We have our indexer that is parsing LEZ blocks. And we have our wallet. So what I did is that I run the node, the indexer, and the sequencer, and I started making some wallet commands. So actually what I did is simple. I just created a public account, and I initialize it, and I claimed some funds from the Pinata program. So what happened is that when I initialized the wallet, the account, sorry, a block number 10 was shown on the sequencer, and it was submitted to the blockchain. Then when I claimed the Pinata program, another block was created, posted on the blockchain, and they were parsed from the indexer. So they are block 10 and block 13. So if we go now to the sequencer, to the block explorer, and here I will just copy paste, for example, the public account. Let me just maybe I will just share my Explorer screen. So what we have here is the blockchain explorer. So we can either put the block ID, for example, the block ID 10, and it will show the hash, it will show the timestamp, and it shows the transaction. So it has one transaction, and this transaction has one account involved, and it was the initialization of the account. If we press on it, we can see the proof size. There is no proof because it's a public transaction. We can see the hash, we can see the program ID, and we can see the account. So if I press on the account, for example, we can see that the balance is 150. Every time that we claim from the Pinata, we are claiming 150 tokens. There is one nonce. This is the program owner. This is the account ID. And here it shows that there are two transactions for this account. So the first transaction, actually, it's the account initialization. And the second one, it shows that there are two accounts involved. Actually, this is the claim. So there are two accounts involved, our public account that we have created and the Pinata account from which we we claimed funds. So it shows that the type of the transaction, the hash, the program ID. It has a small bug here that it's not showing the accounts, but we are fixing it. So yeah, or what we can do is we can put the block ID 13, for example. It will show us, what is it, 14. It's not ours, but like these are the parsed blocks. But yeah, we can also use, instead of the block ID, we can use the hash that it was generated when the block was generated. So if I do this, it will show me the transaction. It will show me also all the information and the account. So yeah. So that was from the LEZ updates, and hopefully we'll see you all soon in the all hands. Thank you.
Awesome. We've come a long way over the past year. It's pretty significant, not even a year. Had a couple questions in the chat we can go through. I think most of these so far are, or all of them are directed at the blockchain part. If you do have questions, put them in the chat. I'll field them now. We've got a little bit of time here. Let's see. Uger had, there's no slash. What is the disincentivization for maliciousness? Thank you.
I mean, okay, so for this question, there's many ways to approach it. So yes, attackers do get an advantage because so the malicious behavior we care about here is double proposing. And so the malicious nodes can try to fork the network, but and it does reduce security of the network, beyond 51%. But it's enough. You take some assumptions on how many malicious nodes you can support, and longest chain will prevail with those assumptions. So even if there is a malicious node trying to double propose, making whenever he wins a slot, he proposes many different blocks forking out the parent using the same lottery win. That will not be enough under some assumptions to break the chain indefinitely. So our finality times are quite long, for example. So we have about 18-hour finality. So that gives longest chain 18 hours to resolve a case where there's enough, to resolve a case where there's malicious behavior trying to fork the network.
Yeah, you have to think about it in terms like Bitcoin's proof of work, but in a proof of stake concept, content, like framing, and having the longer finality time, because like Bitcoin's is around an hour, depending on a hash power. Like it gives you that, like, not only is it transparent that it's happening, you have quite a bit of time to fix it, because you have to sustain that type of thing. Do you know what the percentage or rough percentage is of like stake ownership in order for the chain to keep going?
So it's difficult. Okay, so with the Bitcoin, it's almost exactly the same as Bitcoin, but you reduce it a little bit for this double proposal kind of attacks, because Bitcoin does not have the problem of double proposals, because you have to effectively mine a different block, yeah. Right? It's a bit less than Bitcoin, but it's still better than BFT. So BFT assumes 1/3 faulty, right? So we're doing better than BFT, but it's somewhere between BFT and 51%.
Okay, I'd be curious in looking at that and write an article about it. And maybe looking at those, we've done previous articles on looking at the differences between Bitcoin proof of work and Cryptarchia proof of stake, because it's like I said, it's as close as you can get to the properties of proof of work in a proof of stake context, but there's differences, and I'm really interested in what those like boundaries of the differences are. later as we grow. Let's see. Also, at the end here, Thomas said a lottery winner is also limited in his uses of blend. So like that's another addition onto this that I think is part of the answer.
That's right. Yeah. So blend, you route your block proposals through blend, and we use something like RLN to prevent people from spamming the blend network. And so if you reuse one of those blend RLN tokens, you'll get banned from the network. Like your transaction won't be able to be accepted into the blend network.
Okay.
That's a good point. So the attacker would have to bypass the blend network. So he would have to put his block proposals directly into the network, revealing himself.
That's actually an extra little layer of help with limiting spam or like rate limiting them with that problem by almost forcing the blend. I see what you mean.
Yeah, it helps.
Let's see here. This has to do with your demo with SQLite chain. How do concurrent writes are handled?
So the demo that I showed was a centralized. It's doing the master, like the primary replica model, right? So you have like MySQL, right? You have distributed SQL where you have the primary where you write to, and then you have replica databases that follow the bin logs from the primary. And so we're doing that model there, where you have one single writer, many readers. So concurrent writes there would be just the primary has to order the writes and then write them in the correct order. Once we get to decentralized sequencing, then it gets more interesting because you have many different writers that are writing to the same channel concurrently. And so the way we deal with that is that channels are first write wins. And so if you have different replicas, different like instances writing to the same database, they might have to revert that write and reorg, right, onto whatever was actually accepted on chain. And this is not so different from how traditional web apps are actually done. So like if you receive many HTTP calls going to a web server, that web server is hammering a MySQL database, for example, and there's many concurrent HTTP calls going into that one server that is hammering the MySQL instance. If there's a concurrent write to one row in MySQL, the API server will retry that request, retry the MySQL write sometimes until it goes in. That's one way to do it. But the way that we will probably do it in the end is that, sorry, I'll just finish this.
Yeah.
Sorry, long-winded question answer.
I like long-winded answers.
We will maintain 2 SQLite instances when we have this distributed sequencing. And one is for the finalized state, and then one is for the tip state. And so if you're writing, you write to your tip state and push that to the blockchain. When the blockchain finalizes one transaction, it applies that the indexer will apply that SQL transaction to your finalized SQLite instance. So you have two separate SQLite instances running concurrently. If there's ever a reorg, you throw away your current tip state and replay from the finalized state to the new tip on the new branch that we reorg to. So you have this kind of behavior. It's not so bad. It's not so different from how the EVM deals with it or any other VM. You have to deal with reorgs where you just revert your state and come back to a new state. So this is not going to be an ACID database. This is a decentralized, eventually consistent SQLite database that is globally replicated.
Next question was Joe coming in with asking about SQL Cipher, which is just based on top of SQLite but encrypted.
We have to look at it. I think it should work. It depends how SQL Cipher does the encryption. I imagine it should work.
Yeah, I imagine he's asking because that's what Status uses.
Oh, really?
Yeah. SQL Cipher.
Okay, yeah, I'm not sure exactly how it, if it encrypts the individual, it probably encrypts the database. Okay, yeah, we have to look at it. I'm not sure.
To be continued. Let's see. Nothing else here in terms of questions. So, Daniel, is there anything else you'd like to add, or anything else that you'd like to kind of tack on while we have a few minutes?
No, just thanking the presenters. It was great. Yeah, and hope to see all of you tomorrow.
Yeah. Now everyone is updated with the blockchain side of things, and tomorrow we'll have messaging and storage, which will wrap up the Logos team updates. We also have the ecosystem development engineering team doing a demo or video that I'll then disperse as well, which is useful, I think, on seeing what their efforts have been up to date from their side. And that way, once again, like the more we can kind of front load status reports and updates on how things are right now, the more time we don't have to do that at the all hands, and we can spend together. So thank you all for doing this. Great presentations. The rate in which y'all have been delivering has been awesome and astounding. So thanks, and keep it up.
Great, thank you.
See you tomorrow.
Thank you. Bye.